Today's internet is arguably the largest engineering system ever created by mankind with hundreds of millions of connected computers. Communication links and switches. With billions of users who connected via laptop, tablets and smartphones, and with an array of new internet connected devices such as sensors, webcams, game consoles, picture frames and even washing machines. Given that the internet is so large and has so many diverse components and users, is there any hope of understanding how it works? Are there guiding principles and structure that can provide a foundation for understanding such an amazingly large and complex systems? And if so, is it possible that it actually could be both interesting and fun to learn about computer networks? Fortunately, the answer to all of these questions is resounding yes. Indeed, it is our aim in this book to provide you with the modern introduction to the dynamic field of computer networking, giving you the principles and the practical insights you'll need to understand not only today's network but tomorrow's as well. This first chapter presents a broad overview of computer networking and the internet. Our goal here is to paint a broad picture and set the context for the rest of this book. To see the forest through the trees, we'll cover a lot of ground in the introductory chapter and discuss a lot of pieces of computer network without losing sight of the bigger picture. We'll structure our overview of the computer network in the chapter as follows. After introducing some basic technologies and concepts, we'll first examine the basic hardware and software components that make up a network. We'll begin at the network's edge and look at the end system and network applications running in the network. We'll then explore the core of computer network, examining the links and the switches that transport data, as well as access network and physical media that connects an end system to network core. We'll learn that the internet is a network of networks and we'll learn how these networks connect with each other. After having completed this overview of the edge and the core of the computer network, we'll take a broader and more abstract view of in the second half of the chapter. We'll examine the delay, loss and the throughput of the data in the computer network and provide simple quantitative model for end-to-end throughput and delay. Models that take into account transmission, propagation and queuing delays. Will then introduce some of the key architectural principles in the computer networking, namely protocol layering and service models. We'll also learn that the computer network are vulnerable to many different types of attacks. We'll survey some of these attacks and consider how computer network can be made more secure. And finally, we'll close this chapter with the brief history of computer networking. What is the network? In this book, we'll use the public internet, a specific computer network, as our principal vehicle for discussing the computer network and their protocol. But what is the internet? There are a couple of ways to answer this question. First, we can describe the nuts and the bolts of the internet, that is, the basic hardware and software components of that make up the internet. Second, we can describe the internet in terms of networking infrastructure that provides service to distributed applications. Let's begin with the nuts and bolts description using figure 1.1 to illustrate our discussion.
Section 1.1.1 A nuts and bolts description. The internet is a computer network that interconnects hundreds of millions of computing devices throughout the world. Not too long ago, these computing devices were primarily traditional desktop PCs, Linux workstations and so-called servers that store and transmit information such as web pages and email messages. Increasingly, however, non-traditional internet and end systems such as laptops, smartphones, tablets, TVs, gaming consoles, webcams, automobiles, environmental sensing devices, picture frames, and home electrical and security systems are being connected to the internet. Indeed, the term computer network is beginning to sound a bit dated, given the many non-traditional devices that are being hooked up to the internet. In internet jargon, all of these devices are called hosts and end systems. As of July 2011, there were nearly 850 million end systems attached to the internet ISC 2012, not counting smartphones, laptops and other devices that are only intermittently connected to internet. Overall, there are an estimated 2 billion internet users, ITU 2011. End systems are connected together by a network of communication links and packet switches. We'll see in section 1.2 that there are many types of communication links which are made up of different types of physical media, including coaxial cable, copper wire, optical fiber, and radio spectrum. Different links can transmit data at different rates, with the transmission rate of link measured in bits per second. When one end system has data to send to another end system, the sending end system segments the data and adds header bytes to each segment. The resulting packages of information, known as packets in the jargon of computer networks, are then sent through the network to the destination end system, where they are reassembled into the original data. A packet switch takes a packet arriving on one of its incoming communication links and forwards that packet on one of its outgoing communication links. Packet switches come in many shapes and flavors, but the two most prominent types in today's internet are routers and link layer switches. Both types of switches forward packets towards their ultimate destination. Link layer switches are typically used in access networks, while routers are typically used in the network core. The sequence of communication links and packet switches traversed by a packet from the sending end system to the receiving end system is known as a route or path through the network. The exact amount of traffic being carried in the internet is difficult to estimate, but Cisco VNI 2011 estimates global internet traffic will be nearly 40 exabytes per month in 2012. Packet switch networks, which transport packets, are in many ways similar to transportation networks of highways, roads, and intersections, which transport vehicles. Consider, for example, a factory that needs to move a large amount of cargo to some destination warehouse located thousands of kilometers away. At the factory, the cargo is segmented and loaded into a fleet of trucks. Each of the trucks then independently travels through the network of highways, roads, and intersections to the destination warehouse. At the destination warehouse, the cargo is unloaded and grouped with the rest of the cargo arriving from the same shipment. Thus, in many ways, packets are analogous to trucks. Communication links are analogous to highways and roads. Packet switches are analogous to intersections, and end system are analogous to buildings. Just as a truck takes a path through the transportation network, a packet takes a path through the computer network. End system access the internet through internet service providers, which is also called as ISPs, including residential ISPs such as local cable or telephone companies, corporate ISPs, university ISPs, and ISPs that provide Wi-Fi access in airports, hotels, coffee shops, and other public places. Each ISP is in itself a network of packet switches and communication links. ISPs provide a variety of types of networks access to the end systems, including residential broadband access such as cable modem or DSL, high-speed local area network access, wireless access, and 56 kb per second dial-up modem access. ISPs also provide internet access to content providers, connecting websites directly to the internet. The internet is all about connecting end systems to each other, so the ISPs that provide access to end systems must also be interconnected. These lower tier ISPs are interconnected through national and international upper tier ISPs, such as level 3 communication, AT&T, Sprint, and NTT. An upper tier ISP consists of high-speed routers interconnected with high-speed fiber optic links. Each ISP network, whether upper tier or lower tier, is managed independently, runs the IP protocol, and conforms to certain naming and address conventions. We will examine ISPs and their interconnection more closely in section 1.3. End system, packet switches, and other pieces of the internet run protocols that control the sending and receiving of information within the internet. The transmission control protocol TSP and the internet protocol IP are two of the most important protocols in the internet. The IP protocol specifies the format of the packets that are sent and received among routers and end systems. The Internet's principal protocols are collectively known as TCP or IP. We will begin looking into protocols in which introductory chapter, but that's just a start. Much of this book is concerned with computer network protocols. Given the importance of protocols to the internet, it's important that everyone agree on what each and every protocol does so that people can create systems and products that interoperate. This is where standards come into play. Internet standards are developed by the Internet Engineering Task Force, IETF 2012. The IETF standards documents are called requests for comments, RFCs. RFCs started out as general request for comments, hence the name, to resolve the network and protocol design problems that faced the predecessor to the internet. Alaman 2011. RFCs tend to be quite technical and detailed. They define protocols such as TCP, IP, HTTP, and SMTP for email. There are currently more than 6,000 RFCs. Other bodies also specify standards for network components, most notably for network links. The IEEE 802 LAN or MAN Standards Committee IEEE 802 to 2012, for example, specifies the Ethernet and wireless Wi-Fi standards.
Our discussion about a service description identified many pieces that makes the internet, but we can also describe the internet from the entirely different angle, namely as an infrastructure that provides services to applications. These applications include electronic mail, social networking, instant messaging, voice over IP, distributed games, peer-to-peer file sharing, television over the internet, and much more. The application said to be distributed application, since they involve multiple end systems that exchange the data with each other. Importantly, internet applications run on end system. They don't run in the packet switches in the network core. Although packet switches facilitates the exchange of data among the end system, they are not connected with the application that is source or sink of the data. End systems attached to the internet provides an application programming interface that specify how the program running an end system asks the internet infrastructure to deliver the data to a specific destination program running on the another end system. This internet API means application programming interface is a set of rules that sending program must follow so that internet can deliver the data to the destination program. We will discuss the internet API in the further topics. Now let we understand API with an example. Suppose Alice wants to send letter to Bob using the postal service. Alice of course cannot just write the letter and drop the letter out of their window. Instead, the postal service requires that Alice put the letter in an envelope, write the Bob's full names, address, zip code in the center of the envelope, seal the envelope, put the stamp in the up right hand corner of the envelope, and finally drop the envelope in the official post service mailbox. Thus, the postal service has its own postal service addresses set of rules that Alice must follow to have the postal service deliver to her letter to Bob. In a similar manner, in internet as an API that the program sending data must follow to have the internet deliver the data to the program that will receive the data. The postal service of course provide more than one service to its customer. It provides express delivery, ordinary use, and many more services. In similar manner, the internet provides multiple services to its application. When you develop an internet application, you too must choose one of these internet services for your application. We will discuss the internet services in the further topics. Here we have just two descriptions of the internet. One in terms of its hardware and software components, other in terms of its infrastructure for providing services to the distribution application. But perhaps we are still confused so that what the internet is, what the packet switching, and TCP IP, what is the router, what kind of communication links are present in the internet, what is distributed application, how come the weather sensor is attached to the internet. These all are studied in the further topics.
What is a protocol? Now, that we have got a bit of feel for what the internet is, let's consider another important buzzword in computer networking: protocol. What is a protocol? What does a protocol do? A human analogy. It is probably easiest to understand the notion of a computer network protocol by first considering some human analogies. Since we humans execute protocols all of the time, consider what you do when you want to ask someone for the time of day. A typical exchange is shown in figure. Human protocol, or good manners at least, dictates that one first offer a greeting, the first hi, to initiate communication with someone else. The typical response to a hi is a return hi message. Implicitly, one then takes a cordial hi response as an indication that one can proceed and ask for the time of the day. A different response to initiate hi, such as don't bother me or I don't speak English, or some unprintable reply, might indicate an unwillingness or inability to communicate. In this case, the human protocol would be not to ask for the time of day. Sometimes one gets no response at all to a question, in which case one typically gives up asking the person of the time. Note that in our human protocol, there are specific messages we send and specific actions we take in response to the received reply messages or other events, such as no reply within some given amount of time. Clearly, transmitted and received messages and actions taken when these messages are sent or received or other events occur play a central role in human protocol. If people run different protocols, for example, if one person has a manners but the other does not, or if one understands the concept of time and other does not, the protocols do not interoperate and no useful work can be accomplished. The same is true in networking. It takes two or more communicating entities running the same protocol in order to accomplish a task. Let's consider a second human analogy. Suppose you are in college class, a computer networking class, for example. The teacher is droning on about protocols and you are confused. The teacher stops to ask, are there any questions? A message that is transmitted to and received by all the students who are not sleeping. You raise your hand, transmitting an implicit message to the teacher. Your teacher acknowledges you with a smile, saying yes, a transmitted message encouraging you to ask your question. Teacher love to be asked questions, and you then ask your question, that is, transmit your message to your teacher. Your teacher hears your question, receives your question message and answers, transmit a reply to you. Once again, we see that transmission and receipt of messages and set of conventional actions taken when these messages are sent and received are at the heart of this question and answer protocol. Network protocols. A network protocol is similar to human protocols except that the entities exchanging messages and taking actions are hardware or software components of some device. For example, computers, smartphones, tablet, router, or other network capable devices. All activity in the internet that involves two or more communication remote entities is governed by a protocol. For example, hardware implemented protocols in two physically connected computers control the flow of bits on the wire between the two network interfaces card. Congestion control protocols in end system control the rate at which packets are transmitted between sender and receiver. Protocols in router determines a packet's path from source to destination. Protocols are running everywhere in the internet, and consequently much of this book is about computer network protocols. As an example of computer network protocol with which you are probably familiar, consider what happens when you make request to a web server. That is, when you type the URL of web page into your web browser, The scenario is illustrated in the first. Your computer will send a connection request message to the web server and wait for a reply. The web server will eventually receive your connection request message and return a connection reply message. Knowing that it's now okay to request the VTech document, your computer then sends the name of the web page it wants to fetch from the web server in a get message. Finally, the web server returns the web page to your computer. Given the human and the networking examples above, the exchange of messages and the actions taken when these messages are sent and received are the key defining element of a protocol. A protocol defines the format and the order of messages exchanged between two or more communicating entities, as well as the action taken on the transmission and or receipt of a message or the other event. The internet and computer networks in general make extensive use of protocols. Different protocols are used to accomplish different communication tasks. As you read through this book, you will learn that some protocols are simple and straightforward, while others are complex and intellectually deep. Mastering the field of computer networking is equivalent to understanding the what, why, and how of networking protocols.
Section 1.2, The Network Edge. In the previous section, we presented a high-level overview of the Internet and networking protocols. We are now going to delve a bit more deeply into the components of computer network and the Internet in particular. We begin in this section at the edge of a network and look at the components with which we are most familiar, namely the computers, smartphones, and other devices that we use on a daily basis. In the next section, we'll move from the network edge to the network core and examine switching and routing in the computer networks. Recall from the previous section that in computer networking jargon, the computers and other devices connected to the internet are often referred to as end systems. They are referred to as end systems because they sit at the edge of the internet as shown in the figure 1.3. The internet's end systems include desktop computers, example desktop PCs, Macs, and Linux boxes. Servers, example web and email servers, and mobile computers, example laptops, smartphones, and tablets. Furthermore, an increasing number of non-traditional devices are being attached to the internet as end systems. End systems are also referred to as hosts because they host, that is, run application programs such as web browser program, a web server program, an email client program, or an email server program. Throughout this book, we will use the terms hosts and end system interchangeably. That is, host is equal to end system. Hosts are sometimes further divided into two categories, clients and servers. Informally, clients tends to be desktop and mobile PCs, smartphones, and so on, whereas server tends to be more powerful machines that store and distribute web pages, stream video, relay email, and so on. Today, most of the servers from which we receive search results, email, web pages, videos reside in large data centers. For example, Google has 30 to 50 data centers, with many having more than 100,000 servers.
Access networks. Having considered the applications and end system at the edge of the network, let's next consider the access network. The network that physically connects an end system to the first router on a path from the end system to any other distant end system. Home access, DSL, cable, FTTH, dial up, and satellite. In the developed countries today, more than 65% of households have internet access, with Korea, Netherlands, Finland, and Sweden leading the way with more than 80% of households having internet access, almost all via a high speed broad connection. Finland and Spain have recently declared high speed internet access to a legal right, given the intense interest in home access. Let's begin our overview of access networks by considering how homes connect to the internet. Today, the most prevalent types of broadband residential access are digital subscriber line, which is DSL, and cable. A residency typically obtains DSL internet access from the same local telephone company that provides its wired local phone access. Thus, when DSL is used, a customer's telco is also its ISP. As shown in the figure, each customer's DSL modem uses the existing telephone line to exchange data with a digital subscriber line access multiplexer located in the telco's local central office. The home DSL modem takes digital data and translates it to high frequency tones for transmission over telephone wires to the CO. The analog signals from many such houses are translated back into the digital format at the DSLAM. The residential telephone line carries both data and traditional telephone signals simultaneously, which are encoded at different frequencies. A high-speed downstream channel in the 50 kHz to 1 MHz band, a medium-speed upstream channel in the 4 kHz to 50 kHz band, an ordinary two-way telephone channel in the 0 to 4 kHz band. This approach makes a single DSL like appear as if there were three separate links so that a telephone call and the internet connection can share a DSL link at the same time. On the customer side, a splitter separates the data and telephone signals arriving to the home and forwards the data signal to the DSL modem. On the telco side, in the CO, the DSLAM separates the data and phone signals and sends the data into the internet. Hundreds or even thousands of households connects to the signals DSLAM. The DSL standards define transmission rates of 12 Mbps downstream and 1.8 Mbps upstream, and 24 Mbps downstream and 2.5 Mbps upstream. Because the downstream and upstream rates are different, the access is said to be asymmetric. The actual downstream and the upstream transmission rates achieved may be less than the rates noted above. As a DSL provider, many purposefully limit a residential rate when tiered services are offered, or because the maximum rate can be limited by the distance between the home and the CO. The gauge of a twisted pair line and the degree of electrical interference, engineers have expressly designed DSL for short distances between the home and the CO. Generally, if the residence is not located within 5 to 10 miles of the CO, the residents must resort to an alternative form of internet access. While DSL makes use of telco's existing local telephone infrastructure, cable internet access make use of a cable television company existing cable television infrastructure. A residence obtains cable internet access from the same company that provides its cable television. A fiber optics connects the cable head end to the neighborhood level junctions, from which traditional coaxial cable is then used to reach individual houses and apartments. Each neighborhood junctions typically supports 500 to 5000 homes because both fiber and coaxial cable are employed in this system. It is often referred to as hybrid fiber coax HFC. Cable internet access requires special modems called cable modems. As with a DSL modem, the cable modem is typically an external device and connects to the home PCs through an Ethernet port. At the cable head end, the cable modem termination system, which is CMTS, serves a similar function as a DSL's network, DSLAM, turning the analog signal sent from a cable modems in many downstream homes back into a digital format. Cable modems divide the HFC network into two channels, a downstream and an upstream channel. As with DSL, access is typically asymmetric, with the downstream channel typically allocated a higher transmission rate than the upstream channel. The DOCSIS 2.0 standard defines downstream rates up to 42.8 Mbps and upstream rates of up to 30.7 Mbps. As in case of DSL networks, the maximum achievable rate may not be realized due to lower contracted data rates or media impairments. One important characteristic of cable internet access is that it is shared broadcast medium. In particular, every packet sent to by the head end travels downstream on every link to the every home, and every packet sent by the home travel on the upstream channel to the head end. For this reason, if several users are simultaneously downloading a video file on a downstream channel, the actual rate at which each user receives its video file will be significantly lower than the aggregate cable downstream rate. On the other hand, if there are only a few active users and they are all web surfing, then each of the users may actually receive web pages at a fully cable downstream rate because the users will rarely request a web page at exactly the same time. Because the upstream channel is also shared, a distributed multiple access protocol is needed to coordinate transmission and avoid collisions. Although DSL and cable networks currently represents more than 90% of residential broadband access in the United States, and up and coming technology that promises even higher speed in the deployment of fiber to home FTTH. As the name suggests, the FTTH concept is simple, provide an optical fiber path from the CO directly to the home. In the United States version has been particularly aggressive with FTTH with its FiOS service. There are several competing technologies for optical distribution from the CO to the homes. The simplest optical distribution network is called direct fiber with one fiber leaving the CO for each home. More commonly, each fiber leaving the central office is actually shared by many homes. It is not until the fiber gets relatively close to the homes that it split into individual customer specific fibers. There are two competing optical distribution network architectures that performs its splitting. One is active optical networks and passive optical networks. AON is essentially switched Ethernet, which is discussed in the chapter 5. Each home has an optical network terminator (ONT), which is connected by dedicated optical fiber to a neighborhood splitter. The splitter combines a number of homes onto a single shared optical fiber, which connects to an optical line terminator. In the telco CO, the OLT providing conversion between optical and electrical signals connects to the internet via a telco router. In a homes, user connect the home router to the ONT and access the internet via this home router. In the PON architecture, all packets sent from OLT to a splitter are replicated at the splitter. FTTH can potentially provide internet access rates in the gigabits per second range. However, the most FTTH ISPs provide different rate offerings, with the higher rates naturally costing more money. The average downstream speed of US FTTH customers was approximately 20 Mbps in 2011. Two other access network technologies are also used to provide internet access to the home. In locations where DSL cable and FTTH are not available, a satellite link can be used to connect a residence to the internet at speeds for more than 1 Mbps. Starband and Huggies Net are two such satellite access provider. Dial-up access over traditional phone lines is based on the same model as DSL. A home modem connects over a phone line to a modem in the ISP compared to the DSL and other broadband access network. Dial-up access is extremely slow at 56 kbps.
Access in the enterprise and the home, the Ethernet and Wi-Fi on corporate and university campuses and increasing the home setting. A local area network is used to connect the end system to the edge router. Although there are the many types of LAN technologies, Ethernet is by the far the most prevalent access technology in the corporate, university and the home network. Ethernet user use the twisted pair copper wire to connect the Ethernet switch. Ethernet switch or network such interconnected switch is then turned connected into the largest internet with the Ethernet access. User typically have the 100 Mbps access to the Ethernet switch wherever the server may have the 1 Gbps or even the 10 Gbps access. Increasingly, however, the people are accessing the internet wireless from the laptop, smartphones, tablets, and the other devices. In a wireless LAN settings, the wireless user transmit receive the packets from the access point that is connected into the enterprise network, which is turn into the connected to the wire internet. A wireless LAN user must typically be within a few tens of meter access point. Wireless LAN access based on the IEEE 802.11 technologies. The more colloquially known as Wi-Fi, is now just the about everywhere. Universities, business office, cafes, airports, home, and even in aeroplanes. In many cities, one can stand on the street corner and within a range of 10 or 20 base station. 802.11 has stations that have been discovered and logged on the website by the people who take the great enjoyment in the doing such things. See, today provided the shared transmission rate up to the 54 Mbps. Even though Ethernet and the Wi-Fi access network were the initially developed in the enterprises, corporate, university settings, they have the recently become the relatively common component of the home network. Many homes combine the broadband residential access with those inexpensive wireless LAN technologies to create the powerful home network. This home network consists of a roaming laptop as well as the wired PC, a base station, the wireless access point which is communicates with the wireless PC, a cable modem provide the broadband access to the internet, and the router which is inter allow the household members to have the broadband access to the internet with the one member roaming from the kitchen to the bedrooms. Wide area wireless access 3G and the LTE. Increasingly, devices such as iPhones, Blackberries, Android devices are being used to send the emails, surf web, tweet, and the download music while on the run. These devices employ the same wireless infrastructure used for the cellular telephone and to send and receive the packet through the base station that is operated by the circular network provider. Unlike the Wi-Fi, user need only within a few tens of kilometers as opposed to few tens of meter of the base station. Telecommunication companies have made the enormous investment is so-called third generation is the 3G wireless, which provide the packets which is wide area wireless internet access at the speed in the excess of 1 Mbps. But even the higher speed wide area access technologies of the fourth generation wide area wireless network are the already being developed. LTE for long term evaluation, a candidate for the Bad Acronomy of the Year award, has its root in 3G technology and can potentially achieve rates in excess of 10 Mbps. LTE downstream rates many tens of Mbps have been reported in the commercial development. We'll cover the basic principle of wireless network and mobility as well as the Wi-Fi, 3G, LTE technologies. Thank you.
Physical media. In the previous subsection, we gave an overview of some of the most important network access technologies in the internet. As we described these technologies, we also indicated the physical media used. For example, we said that HFC uses a combination of fiber cables and coaxial cable. We said that DSL and Ethernet use copper wire. And we said that mobile access network use the radio spectrum. In this subsection, we provide a brief overview of these and other transmission media that are commonly used in the internet. In order to define what is meant by a physical medium, let us reflect on the brief life of a bit. Consider a bit traveling from one end system through a series of links and routers to another end system. This poor bit get kicked around and transmitted many times. The source end system
first transmits the bit and shortly thereafter the first router in the series receives the bit. The first router then transmits the bit and shortly thereafter the second router receives the bit, and so on. Thus, our bit when traveling from source to destination passes through a series of transmitter-receiver pairs. For each transmitter-receiver pair, the bit is sent by propagating electromagnetic waves or optical pulses across a physical medium. The physical medium can take many shapes and forms and does not have to be the same type for each transmitter-receiver pair along the path. Examples of physical media include twisted pair copper wire, coaxial cable, multi-mode fiber optic cable, terrestrial radio spectrum, and satellite radio spectrum. Physical media fall into two categories: guided media, unguided media. With guided media, the waves are guided along a solid medium, such as a fiber optic cable, a twisted pair copper wire, or a coaxial cable. With unguided media, the waves propagate in the atmosphere and in outer space, such as in a wireless LAN or a digital satellite channel. But before we get into the characteristics of various media types, let us say a few words about their costs. The actual cost of physical link, copper wire, fiber optic cable, and so on is often relatively minor compared to other networking costs. In particular, the labor cost associated with installation of physical link can be order or magnitude higher than the cost of material. For this reason, many builders install twisted pair optical fiber and coaxial in every room in building. Even if only one medium is initially used, there is good chance that another medium could be in the near future, and so money is saved not having to lay additional wires in the future. Twisted pair copper wire. The least expensive and most commonly used guided transmission medium is twisted pair copper wire. For over 100 years, it has been used by telephone network. In fact, more than 99% of the wire connections from the telephone handset to local telephone switch use twisted pair copper wire. Most of us have seen twisted pair in our homes and work environments. Twisted pair consists of two insulated copper wires, each about 1 mm thick, arranged in a regular spiral pattern. The wires are twisted together to reduce the electrical interference from similar pair close by. Typically, a number of pair are bundled together in a cable or wrapping the pair in a protective shield. A wire pair constitutes a single communication link. Unshielded twisted pair (UTP) is commonly used for computer network within a building, that is, for LANs. Data rate for LANs using twisted pair ranges from 10 Mbps to 10 Gbps. The data rates that can be achieved dependent on the thickness of the wire and the distance between transmitter and receiver. When fiber optic technology emerged in 1980s, many people disparaged twisted pair because of its relatively low bit rates. Some people even felt that fiber optic technology will completely replace twisted pair. But twisted pair did not give up so easily. Modern twisted pair technologies such as Category 6A cable can achieve data rates of 6 Gbps for distance up to 100 meters. In the end, twisted pair has emerged a dominant solution for high-speed LAN networking. As discussed earlier, twisted pair is also commonly used for residential internet access. We saw that dial-up modern technology enable access at rate up to 56 kbps over twisted pair. We also saw that DSL digital subscriber line technology has enabled residential users to access the internet in 10 of Mbps over twisted pair when users live close to the ISP's modem.
Coaxial cable. Like twisted pair cable, coaxial cable consists of two copper conductors, but two conductors are concentric rather than parallel. With this construction, special insulation and shielding, coaxial cable can achieve high data transmission rates. Coaxial cables is quite common in cable television systems. As we saw earlier, cable television systems have recently been coupled with cable modem to provide residential users with internet access at a rate of tens of MB per second. In cable television and cable internet access, the transmitter shifts the digital signal to a specific frequency band, and the resulting analog signals is sent from the transmitter to one or more receivers. Coaxial cables can be used as a guided shared medium, especially a number of N systems can be connected directly to a cable, with each of N systems receiving whatever is sent by the other N systems. Fiber optics. An optical fiber is a thin, flexible medium that conducts a pulse of light, with each pulse representing a bit. A bit optical fiber can support a tremendous bit rates up to a tens or even hundreds of a gigabits per second. They are immune to electromagnetic interferences, have very low signal attenuation up to 100 kilometers, and are very hard to tap. These characteristics have made fiber optics the preferred longitudinal guided transmission media, particularly for overseas links. Many of the long distance telephone networks in United States elsewhere now use fiber optics exclusively. Fiber optics is also prevalent in a backbone of internet. However, the high cost of optical devices such as transmitter, receiver, and switches has hindered their deployment for a short-haul transport, such as in LAN or in the home in a residential access network. The optical carrier OC standard link speeds range from 51.8 MB per second to 39.8 gigabyte per second. These specifications are often referred to as OCN, where the link speed equals to n into 51.8 MB per second. Standards in use today include OC1, OC3, OC12, OC24, OC2048, OC96, OC192, OC768 provide a coverage of various aspects of optical networking. Terrestrial radio channels. Radio channels carry signals in an electromagnetic spectrum. They are attractive medium because they require no physical wire to be installed. Can penetrate walls, provide a connectivity to a mobile user, and can potentially carry a signal for long distances. The characteristics of a radio channel depends significantly on the propagation environment and the distance over which a signal is to be carried. Environmental considerations determine path loss, shadow fading, which decreases the signal strength as a signal travels over a distance and around or through obstructing objects, and a multi-path fading. It means due to signal reflection of the interfering objects and interferences. It is due to other transmissions and electromagnetic signals. These are the three reasons, and terrestrial radio channels can be broadly classified into three groups. Those are operate over those that operate over a very short distance, that is with 1 or 2 meters, and those that operate in local areas, typically spanning from 10 to a few hundred meters, and those that operate in a wide area spanning tens of kilometers. Personal devices such as wireless handset, keyboards, and medical devices operate over a short distances, and the wireless LAN technologies described in section 121 use a local area radio channels. The cellular access technologies use wide area radio channels. We'll discuss radio channels in details in chapter 6. Satellite radio channels. A communication satellite links two or more earth-based microwave transmitters or receivers known as Ground stations. The satellite receives a transmission on one frequency band, regenerates the signal using a repeater, and transmitter the signals on other frequency. Two types of satellites are used in communication: geostationary satellites and low Earth orbit or LEO satellites. Geostationary satellites permanently remain above the same spot on the Earth. This stationary presence is achieved by the placing the satellite in orbit at the 36,000 kilometers above the Earth's surface. This huge distance from ground stations throws satellite back to ground station introduces a substantial signal propagation delay of 280 million milliseconds. Nevertheless, satellite links which can operate at a speed of hundreds of MB per second are often used in areas without access to DSL or cable-based internet access. LEO satellites are placed much closer to Earth and do not remain permanently above the spot on Earth. They rotate around Earth just as the moon does and may communicate with each other as well as with ground stations to provide a continuous coverage to an area. Many satellites need to be placed in orbit. There are currently many low altitude communication systems in development. Layout satellite constellation web page Wood 2012 provide and collects information on satellite constellation systems for communications. LEO satellite technology may be used to internet access sometimes in the future.
The network core. Having examined the internet's edge, let us now delve more deeply inside the network core, the mesh of packets, switches, and links that interconnects the internet's end system. Packet switching. In a network application, end system exchange messages with each other. Messages can contain anything the application designer wants. Messages may perform a control function. For example, hi message in our handshaking example, or can contain data such as an email message, a JPEG image, or an MP3 audio file. To send a message from a source end system to a destination end system, the source breaks long messages into smaller chunks of data known as packets. Between source and destination, each packet travels through communication links and packet switches, for which there are two predominant types: routers and link layer switches. Packets are transmitted over each communication link at a rate equal to the full transmission rate of the link. So, if a source end system or a packet switch is sending a packet of L bits over a link with transmission rate R bits per second, then the time to transmit the packet is L by R seconds. Store and forward transmission. Most packet switches use store and forward transmission at the inputs to the links. Store and forward transmission means that the packet switch must receive the entire packet before it can begin to transmit the first bit of packet onto the outbound link. To explore store and forward transmission is more detailed, consider a simple network consisting of two end systems connected by a single router. A router will typically have many incident links, since its job is to switch an incoming packet onto an outgoing link. In this example, the router has the simple task of transferring a packet from one link to the only other attached link. In this example, the source has three packets, each consisting of L bits to send the destination. At the snapshot of time shown in figure, the source has transmitted some of packets 1 and the front of packet 1 has already arrived at the router. Because the router employs store and forwarding at this instant of time, the router cannot transmit the bits it has received. Instead, it must first buffer the packet's bits. Only after the router has received all the packet's bits can it begin to transmit the packet onto the outbound link. To gain some insight into store and forward transmission, let's now calculate the amount of time that elapses from when the source begins to send the packet until the destination has received the entire packet. Here we will ignore the propagation delay, the time it takes for the bits to travel across the wire at near the speed of light. The source begins to transmit at time 0. At time L by R seconds, the source has transmitted the entire packet and the entire packet has been received and stored at the router. At time L by R seconds, since the router has just received the entire packet, it can begin to transmit the packet onto the outbound links towards the destination. At time 2L by R, the router has transmitted the entire packet and the entire packet has been received by the destination. Thus, the total delay is 2L by R. If the switch instead forwarded bits as soon as they arrive without first receiving the entire packet, then the total delay would be L by R. Since bits are not held up at the router, but as we discuss, routers need to receive, store and process the entire packet before forwarding. Now let's calculate the amount of time that elapses from when the source begins to send the first packet until the destination has received all three packets. As before, at time L by R, the router begins to forward the first packet, but also at time L by R, the source will begin to send the second packet since it has just finished sending the entire first packet. Thus, at time 2L by R, the destination has received the first packet and the router has received the second packet. Similarly, at time 3L by R, the destination has received the first two packets and the router has received the third packet. Finally, at time 4L by R, the destination has received all three packets. Let's now consider the general case of sending one packet from source to destination over a path consisting of n links, each of rate r. Thus, there are n minus 1 routers between source and destination. Applying the same logic as above, we see that the end-to-end delay is d is equals to n into L by r.
Queuing delays and packet loss. Each packet switch has multiple links attached to it. For each attached link, the packet switch has an output buffer, also called an output queue, which stores packets that the router is about to send into that link. The output buffer plays a key role in packet switching. If an arriving packet needs to be transmitted onto a link but finds the link busy with the transmission of another packet, the arriving packet must wait in the output buffer. Thus, in addition to the store and forward delays, packets suffer output buffers queuing delays. These delays are variable and depend on the level of congestion in the network. Since the amount of buffer space is finite, an arriving packet may find the buffer is completely full with other packets waiting for transmission. In this case, packet loss will occur. Either the arriving packet or one of the already queued packet will be dropped. Figure 1.12 illustrates a simple packet switch network. As in figure 1.11, packets are represented by three-dimensional slabs. The width of the slab represents the number of bits in the packet. In the figure, all packets have the same width and hence the same length. Suppose host A and host B are sending packets to host E. Host A and B first sends their packets along 10 Mbps Ethernet links to the first router. The router then directs these packets to the 1.5 Mbps link. If during a short interval of time the arrival rate of packets to the router exceeds 1.5 Mbps, congestion will occur at the router as packets queue in the link's output buffer before being transmitted onto the link. For example, if host A and B each send a burst of 5 packets back to back at the same time, then most of these packets will spend some time waiting in the queue. The situation is, in fact, entirely analogous to many common day situations. For example, when we wait in line for a bank teller or wait in front of the toll booth, we'll examine this queuing delay in more detail in section 1.4. Forwarding tables and routing protocols. Earlier, we said that a router takes a packet arriving on one of its attached communication links and forwards that packet onto another one of its attached communication links. But how does the router determine which link it should forward the packet onto? The packet forwarding is actually done in different ways in different types of computer networks. Here, we briefly describe how it is done in the internet. In the internet, every end system has an address called as IP address. When a source end system wants to send a packet to the destination end system, the source includes the destination's IP address in the packet's header. As with postal addresses, this addresses has a hierarchical structure. When a packet arrives at a router in the network, the router examines a portion of the packet's destination address and forwards the packet to the adjacent router. More specifically, each router has a forwarding table that maps destination addresses to tell other routers outbound links. When a packet arrives at a router, the router examines the address and searches its forwarding table. Using this destination address to find the appropriate outbound link, the router then directs the packet to this outbound link.
Circuit switching. There are two fundamental approaches to moving data through a network of links and switches: circuit switching and packet switching. Having covered packet switch network in the previous subsection, we now turn our attention to circuit switch network. In circuit switch network, the resources needed along a path to provide for a communication between the end system are reserved for the duration of a communication session between the end system. In packet switch network, these resources are not reserved. A session message uses the resources on demand and as a consequence may have to wait for access to a communication link. As a simple analogy, consider two restaurants, one that required reservation and another that neither required reservation nor accept them. For the restaurant that required reservation, we have to go through the hassle of calling before we have leave home, but when we arrived at the restaurant, we can in a principle immediately be seated and order our meal. For the restaurant that does not require reservation, we don't need to bother to reserve a table, but when we arrived at the restaurant, we may have to wait for the table before we can be seated. Telephone network are example of circuit switch network. Consider what happens when one person wants to send the information to another over a telephone network. Before the sender can send the information, the network must establish a connection between the sender and the receiver. This is a bona fide connection for which the switches on the path between the sender and receiver maintain a connection state. For that connection, in the jargon of telephony, this connection is called a circuit. When the network establishes the circuit, it also reserves a constant transmission rate in the network link for the duration of connection. Since a given transmission rate has been reserved for the sender to receiver connection, the sender can transfer the data to the receiver at the guaranteed constant rate. Figure 1.13 illustrates a circuit switch network. In this network, 4 circuit switches are interconnected by 4 links. Each of these links has 4 circuits so that each link can support 4 simultaneous connections. The hosts are each directly connected to one of the switches. When two hosts want to communicate, the network established a dedicated end-to-end connection between the two hosts. Thus, in order for host A to communicate with host B, the network must first reserve one circuit on each of the two links. In this example, the dedicated end-to-end connection used the second circuit in the first link and fourth circuit in the second link. Because each link has 4 circuits for each link used by the end-to-end connection, the connection get 1/4 of the link total transmission capacity for the duration of the connection. Thus, for example, if each link between the adjacent switches has a transmission rate of 1 Mbps, then each end-to-end circuit switches connection get 250 kbps of dedicated transmission rate. Next, consider what happens when one host wants to send a packet to another host over a packet switch network such as the internet. As with circuit switching, the packet is transmitted over a series of a communication link, but different from circuit switching, the packet is sent to the network without reserving any link resources whatsoever. If one of these link is congested because other packet need to be transmitted over the link at the same time, then the packet will have to wait in a buffer at the sending side of the transmission link and suffer a delay. The internet makes its best effort to deliver the packet in a timely manner, but it does not make any guarantees.
Multiplexing in circuit switched networks. A circuit in a link is implemented with either frequency division multiplexing or time division multiplexing. With FDM, the frequency spectrum of a link is divided up among the connections established across the link. Specially, the link dedicates a frequency band to each connection for the duration of the connection. In telephone networks, this frequency band typically has a width of 4 kHz. The width of band is called, not surprisingly, the bandwidth. FM radio stations also use FDM to share the frequency spectrum between 88 MHz to 108 MHz, with each station being allocated a specific frequency band. For a TDM link, time is divided into frames of fixed duration, and each frame is divided into a fixed number of time slots. When the network establishes a connection across a link, the network dedicates one time slot in every frame to this connection. These slots are dedicated for the sole use of that connection, with one time slot available for use to transmit the connection's data. For example, FDM and TDM for a specific network link supporting up to 4 circuits. For FDM, the frequency domain is segmented into 4 bands. Each of bandwidth is 4 kHz. For TDM, the time domain is segmented into frames with 4 time slots in each frame. Each circuit is assigned the same dedicated slot in the revolving TDM frames. For TDM, the transmission rate of circuit is equal to frame rate multiplied by the number of bits in a slot. For example, if the link transmits 8000 frames per second and each slot consists of 8 bits, then the transmission rate of each circuit is 64 kilobits per second. Proponents of packet switching have always argued that circuit switching is wasteful because the dedicated circuits are idle during silent periods. For example, when one person in a telephone call stops talking, the idle network resources cannot be used by other ongoing connections. As another example of how these resources can be underutilized, consider a radiologist who uses a circuit switched network to remotely access a series of X-rays. The radiologist sets up a connection, requests an image, contemplates the image, and then requests a new image. Network resources are allocated to connection but are not used during the radiologist contemplation periods. Proponents of packet switching also enjoy pointing out that establishing end-to-end circuits and reserving end-to-end transmission capacity is complicated and requires complex signaling software to coordinate the operation of switches along the end-to-end path. Before we finish our discussion of circuit switching, let us work through a numerical example that should shed further insight on the topic. Let us consider how long it takes to send a file of 640,000 bits from host A to host B over a circuit switched network. Suppose that All links in the network use TDM with 24 slots and have a bit rate of 1.536 Mbps. Also, suppose that it takes 500 milliseconds to establish an end-to-end circuit before host A can begin to transmit the file. How long it takes to send the file? Each circuit has a transmission rate of 64 kbps, so it takes 10 seconds to transmit the file. To this 10 seconds, we add the circuit establishment time, giving 10.5 seconds to send the file. Note that transmission time is independent of number of links. The transmission time would be 10 seconds if the end-to-end circuit passed through one link or 100 links. Packet switching versus circuit switching. Having described circuit switching and packet switching, let us compare the two. Critics of packet switching have often argued that packet switching is not suitable for real-time services because of its variable and unpredictable end-to-end delays. Proponents of packet switching argue that it offers better sharing of transmission capacity than circuit switching. It is simpler, more efficient and less costly to implement than circuit switching. An interesting discussion of packet switching versus circuit switching is, generally speaking, people who do not like to hassle with restaurant reservations prefer packet switching to circuit switching. Why is packet switching more efficient? Let us look at the simple example. Suppose users share a 1 Mbps link. Also, suppose that each user alternates between periods of activity. When a user generates data at a constant rate of 100 kbps and periods of inactivity when a user generates no data. Suppose further that a user is active only 10% of the time. With circuit switching, 100 kbps must be reserved for each user at all times. For example, with circuit switched TDM, if a 1 second frame is divided into 10 time slots of 100 millisecond each, then each user would be allocated 1 time slot per frame. The circuit switched link can support only 10 simultaneous users. With packet switching, the probability that a specific user is active is 0.1. If there are 35 users, the probability that there are 11 or more simultaneous active users is approximately 0.0004. When there are 10 or fewer simultaneous active users, the aggregate arrival rate of the data is less than or equal to 1 Mbps, the output rate of the link. Thus, when there are 10 or fewer active users' packets flow through a link essentially without delay, as is the case with circuit switching. When there are more than 10 simultaneous active users, then the aggregate arrival rate of packets exceeds the output capacity of the link, and the output queue will begin to grow. Because the probability of having more than 10 simultaneously active users is minuscule in this example. Packet switching provides essentially the same preferences as circuit switching, but does so while allowing for more than 3 times the number of users. Let us now consider a second simple example. Suppose there are 10 users and that one user suddenly generates 1000 bit packets, while other users remain quiescent and do not generate packets. Under TDM, circuit switching with 10 slots per frame and each slot consisting of 1000 bits. The active user can only use its one time slot per frame to transmit data, while the remaining 9 time slots in each frame remains idle. It will be 10 seconds before all of the active users' 1 million bits of the data has been transmitted. In the case of packet switching, the active users can continuously send its packets at the full link rate of 1 Mbps. since there are no other users generating packets that need to be multiplexed with the active users packets. In this case, all of the active user data will be transmitted within 1 second. The above examples illustrate two ways in which the preferences of the packet switching can be superior to that of circuit switching. They also highlight the crucial difference between the two forms of sharing a link's transmission rate among multiple data streams. Circuit switching pre-allocates use of transmission link regardless of demand, with allocated but unneeded link time going unused. Packet switching, on the other hand, allocates link use on demand. Link transmission capacity will be shared on the packet by packet basis only among those users who have packets that need to be transmitted over the link. Although packet switching and circuit switching are both prevalent in today's telecommunication networks, the trend has certainly been in the direction of packet switching. Even many of the today's circuit switched telephone networks are slowly migrating towards packet switching. In particular, telephone networks often use packet switching for the expensive overseas portion of the telephone call.
The next topic, 1.3.3, a network of networks. We saw earlier that end systems like PCs, smartphones, web servers, mail servers, and so on connect into the internet via an access ISP. The access ISP can provide either wired or wireless connectivity using an array of access technologies including DSL, cable, FTTH, Wi-Fi, and cellular. Note that the access ISP does not have to be a teleco or a cable company. Instead, it can be, for example, a university providing internet access to students, staff, and faculty, a company providing access for its employees. But connecting end users and connect providers into an access ISP is only a small piece of solving the puzzle of connecting the billions of end systems that make up the internet. To complete this puzzle, the access ISP themselves must be interconnected. This is done by creating a network of networks. Understanding this phrase is the key to understanding the internet. Over the years, the network of networks that forms the internet has evolved into a very complex structure. Much of this evolution is driven by economics and national policy, rather than by performance considerations. In order to understand today's internet network structure, let's incrementally build a series of network structure, with each new structure being a better approximation of complex internet that we have today. Recall that overreaching goal is to interconnect the access ISPs so that all end systems can send packets to each other. One new approach would be to have each access ISPs directly connect with every other access ISPs. Such a mesh design is, of course, much too costly for the access ISPs, as it would require each access ISP to have a separate communication link to each of the hundreds of thousands of other access ISPs all over the world. Our first network structure 1, interconnects all of the access ISPs with a single global transist ISP. Our global transist ISP is a network of routers and communication links that not only spans the globe, but also has at least one router near each of the hundreds of thousands of access ISPs. Of course, it would be very costly for the global ISP to build such an extensive network. To be profitable, it would naturally charge each of the access ISPs for connectivity, within the pricing reflecting, but not necessarily directly proportional to, the amount of traffic an access ISP exchanges with the global ISP. Since the access ISP pays the global transist ISP, the access ISP is said to be a customer and the global transist ISP is said to be a provider. company builds and operates a global transit ISP that is profitable, then it is natural for other companies to build their own global transit ISPs and compete with the original global transit ISP. This leads to network structure 2, which consists of hundreds of thousands of access ISPs and multiple global transit ISP. The access ISPs certainly prefer network structure 2 over network structure 1, since they now choose among the competing global transit providers as a function of their pricing and services. Note, however, that the global transit ISPs themselves must interconnect. Otherwise, access ISPs connect to one of the global transit providers would not be able to communicate with the access ISPs connected to the other global transit providers. Network structure 2, just described, is a two-tier hierarchy with a global transit providers residing at the top tier and access ISPs at the bottom tier. This assumes that global transit ISPs are not only capable of getting close to each and every access ISPs, but also find it economically desirable to do so. In reality, although some ISPs do have impressive global coverage and do directly connect with many access ISPs, no ISP has presence in each and every city in the world. Instead, in any given region, there may be a regional ISP to which the access ISPs in the region connect. Each regional ISP then connects to Tier 1 ISPs. Tier 1 ISP are similar to company, our imaginary global transit ISP, but Tier 1 ISP, which actually do exist, do not have a presence in every city in the world. There are approximately a dozen Tier 1 ISPs, including Level 3 Communications, AT&T, Sprint, and NTT. Interestingly, no group officially sanctions Tier 1 status. As the saying goes, if you have to ask if you are a member of a group, you are probably not. Returning to this network of networks, not only are three multiple competing Tier 1 ISPs, there may be multiple competing regional ISPs in the region. In such a hierarchy, each access ISP pays a regional ISP to which it connects, and each regional ISP pays the Tier 1 ISP to which it connects. An access ISP can also connect directly to the Tier 1 ISP, in which case it pays the Tier 1 ISP. Thus, this customer-provider relationship at each level of the hierarchy. Note that the Tier 1 ISP do not pay anyone. There may be a larger regional ISPs, possibly spanning an entire country, to which the smaller regional ISPs in that region connect. The larger regional ISPs then connects to a Tier 1 ISP. For example, in China, there are access ISPs in each city, which connect to provincial ISPs, which in turn connect to national ISP, which finally connect to Tier 1 ISPs. We refer to this multi-tier hierarchy, which is still only a pure approximation of today's internet, as network structure 3. To build a network that more closely resembles today's internet, we must add points of presence, POPs, multiple homing, PoE, and Internet Exchange Points, IXPs, to the hierarchical network structure 3. POPs exist in all levels of the hierarchy, except for the bottom of level. A POP is simply a group of one or more routers at the same location in the provider's network where customer ISPs can connect into the provider ISP. For customer network to connect to a provider POPs, it can lease a high-speed link from the third-party telecommunications provider to directly connect one of its routers to a routers at a POP. Any ISP, except for Tier 1 ISPs, may choose to multi-home, that is, to connect to a more provider ISPs. So, for example, an access ISP may multi-home with the two regional ISPs, or it may multi-home with the two regional ISPs, and also with a Tier 1 ISP. Similarly, a regional ISP may multi-home with multi-Tier 1 ISPs. When ISPs multi-homes, it can continue to send and receive packets into the internet even if one of its providers has a failure. As we just learned, customer ISP pay their provider ISPs to obtain global internet interconnectivity. The amount that a customer ISP pays a provider ISP reflects the amount of traffic it exchanges with the provider. To reduce these costs, a pair of nearby ISPs at the same level of hierarchy can peer. That is, they can directly connect their networks together so that all traffic between them passes over the direct connection rather than through upstream intermediaries. When two ISPs peer, it is typically settlement free. That is, neither ISP pays the other. As noted earlier, Tier 1 ISPs also peer with one another. Settlement free. For a readable discussion of peering and customer-provider relationships, see Vanderburg in 2008. Along the same lines, a third-party company can create an Internet Exchange Point, IXP, typically in a standalone building with its own switches, which is a meeting point where multiple ISPs can be together. There are roughly 300 IXPs in the Internet today. We refer to this ecosystem consisting of access ISPs, regional ISPs, Tier 1 ISPs, POPs, multiple homing, peering, and IXPs as network structure 4. Now we finally are at network structure 5, which describes the Internet of 2012. Network structure 5, illustrated in figure 1.15, builds at top of the network structure 4 by adding content provider networks. Google is currently one of the leading examples of such a content provider network. As of this citing, it is estimated that Google has 30 to 50 data centers distributed across North America, Europe, Asia, South America, and Australia. Some of these data centers housing over 100,000 servers, which other data centers are smaller, housing only 100 of the servers. The Google data centers are all interconnected via Google private TCP/IP network, which spans the entire globe but is nevertheless separate from the public internet. Importantly, the Google private network only carries traffic to from Google services. As shown in figure 1.15, the Google private network attempts to bypass the upper tiers of the internet by peering settlement-free with low-tier ISPs, either by directly connecting with them or by connecting with them at IXPs. However, because many access ISPs can still only be reached by transiting through Tier 1 networks, the Google network also contains two Tier 1 ISPs and pays those ISPs for the traffic it exchanges with them. By creating its own network, a content provider not only reduces its payments to upper tier ISPs, but also has greater control of how its services are ultimately delivered to end users. Google's network infrastructure is described in greater detail in section 7.2.4. In summary, today's internet, A network of networks is complex, consisting of a dozen or so tier 1 ISPs and hundreds of thousands of low tier ISPs. The ISPs are diverse in their coverage, with some spanning multiple continents and oceans, and others limited to narrow geographic regions. The lower tier ISPs connect to the higher tier ISPs, and the higher tier ISPs interconnect with one another. Users and connect providers are customers of low tier ISPs, and low tier ISPs are customers of high tier ISPs. In recent years, major content providers have also created their own networks and connect directly into low tier ISPs where possible.
1.4 Delay, loss, and throughput in packet switched network. Back in section 1.1, we said that the internet can be viewed as an infrastructure that provides services to distributed applications running on end systems. Ideally, we would like internet services to be able to move as much data as we want between any two end systems instantaneously without any loss of data. Alas, this is a lofty goal, one that is unachievable in reality. Instead, computer networks necessarily constrain throughput, the amount of data per second that can be transferred between end systems, introduce delays between end systems, and can actually lose packets. On one hand, it is unfortunate that the physical laws of reality introduce delay and loss as well as constrained throughput. On the other hand, because computer networks have these problems, there are many fascinating issues surrounding how to deal with the problems. More than enough issues to fill a course on computer networking and to motivate thousands of PhDs. In this section, we will begin to examine and quantify delay, loss, and throughput in computer networks. 1.4.1 Overview of delay in packet switched networks. Recall that a net packet starts in a host, the source, passes through a series of routers, and ends its journey in another host, the destination. As the packet travels from one node, host or router to subsequent node along this path, the packet suffers from several types of delays at each node along the path. The most important of these delays are the nodal processing delay, queuing delay, transmission delay, and the propagation delay. Together, these delays accumulate to give a total nodal delay. The performance of many internet applications such as search, web browsing, email, maps, instant messaging, and voice over IP are greatly affected by network delays. In order to acquire a deep understanding of packet switching and computer networks, we must understand the nature and importance of these delays. Types of delay. Let's explore these delays in the context of figure 1.16. As part of its end-to-end route between source and destination, a packet is sent from the upstream node through router A to router B. Our goal is to characterize the nodal delay at router A. Note that router A has an outbound link leading to router B. This link is preceded by a queue, also known as a buffer. When the packet arrives at router A from the upstream node, router A examines the packet's header to determine the appropriate outbound link for the packet and then directs the packet to this link. In this example, the outbound link for the packet is the one that leads to router B. A packet can be transmitted on a link only if there is no other packet currently being transmitted on the link. If there are no other packets preceding it in the queue, if the link is currently busy, or if there are other packets already queued for the link, the newly arriving packet will join the queue. Processing delay. The time required to examine the packet's header and determine where to direct the packet is part of the processing delay. The processing delay can also include other factors such as the time needed to check for bit level errors in the packet that occurred in transmitting the packet's bits from the upstream node to router A. Processing delays in high-speed routers are typically on the order of microseconds or less. After this nodal, the router directs the packet to the queue that precedes the link to router B. Queuing delay. At the queue, the packet experiences a queuing delay as it waits to be transmitted onto the link. The length of the queuing delay of a specific packet will depend on the number of earlier arriving packets that are queued and waiting for transmission onto the link. If the queue is empty and no other packet is currently being transmitted, then our packet's queuing delay will be zero. On the other hand, if the traffic is heavy and many other packets are also waiting to be transmitted, the queuing delay will be long. We will shortly we will see shortly the number of packets that an arriving packet might expect to find is a function of the intensity and nature of the traffic arriving at the queue. Queuing delays can be on the order of microseconds to milliseconds in practice. Transmission delay. Assuming that the packets are transmitted in a first come first served manner, as in common in packet switch networks, or packet can be transmitted only after all the packets that have arrived before it have been transmitted. Denote the length of the packets by L bits and denote the transmission rate of the link from router A to router B by R bits per second. For example, for a 10 MB per second Ethernet link, the rate is 10 MB per second. For 100 MB per second Ethernet link, the rate is 100 MB per second. The transmission delay is L by R. This is the amount of time required to push, that is, transmit all the packets bits into this link. Transmission delays are typically on the order of microseconds to milliseconds in practice. Propagation delay. Once a bit is pushed into the link, it needs to propagate to router B. The time required to propagate from the beginning of the link to router B is the propagation delay. The bit propagates as the propagation speed of the link. The propagation speed depends on the physical medium of the link, that is fiber optics, twisted pair copper wire, and so on, and is as in the range of 2 into 10 to the power 8 meter per second to 3 into 10 to the power meter per second, which is equal to or a little less than the speed of the light. The propagation delay is the distance between two rotors divided by the propagation speed. That is, the propagation delay is d by s, where d is the distance between rotor A and the rotor B, and s is the propagation of speed of the link. Once the last bit of the packet propagates to the node B, it and all the preceding bits of the packets are stored in rotor B. The whole process then continues with the rotor B now performing the forwarding. In wide area networks, propagation delays are on the order of milliseconds. Comparing transmission and propagation delay. Newcomers to the field of computer networking sometimes have difficulty understanding the difference between transmission delay and propagation delay. The difference is subtle but important. Transmission delay is the amount of time required for the router to push out the packet. It is a function of packet's length and the transmission rate of the link, but has nothing to do with the distance between two routers. The propagation delay, on the other hand, is the time it takes a bit to propagate from one router to the next. It is a function of the distance between two routers, but has nothing to do with the packet's length or the transmission rate of the link. An analogy might clarify the notions of transmission and propagation delay. Consider a highway that has toll booth every 100 kilometers, as shown in figure 1.17. You can think of the highway segments between toll booths as links and the toll booths as routers. Suppose that cars travel, that is propagate on the highway at a rate of 100 km per hour. That is, when car leaves a toll booth, it instantaneously accelerates to 100 km per hour and maintains the speed between toll booths. Suppose next 10 cars traveling together as a caravan follow each other in a fixed order. You can think of each car as a bit and a caravan as a packet. Also suppose that each toll booth services, that is, transmits a car at the rate of one car per 12 seconds, and that is late at night, so that the caravan's cars are the only cars on the highway. Finally, suppose that whenever the first car of the caravan arrives at the toll booth, it waits at the entrance until the other 9 cars have arrived and lined up behind it. Thus, the entire caravan must be stored
at the toll booth before it going begin to forward. The time required for the toll booth to push the entire caravan onto the highway is 10 cars by 5 cars per minute is equal to 2 minutes. This time is analogous to the transmission delay in a rotor. The time required for a car to travel from the exit of one toll booth to the next toll booth is 100 km by 100 km per hour is equal to 1 hour. This time is analogous to propagation delay. Therefore, the time from when the caravan is stored in front of the toll booth until the caravan is stored in front of the next toll booth is the sum of transmission delay and propagation delay. In this example, 62 minutes. Let's explore this analogy a bit more. What would happen if toll booth service time for a caravan were greater than the time for a car to travel between the toll booths? For example, suppose now the cars travel at the rate of 1000 km per hour and the toll booth services cars at the rate 1 car per minute. Then the traveling delay between two toll booths is 6 minutes and the time to serve a caravan is 10 minutes. In this case, first few cars in the caravan will arrive at the second toll booth before the last cars in the caravan leave the first toll booth. This situation also arises in packet switch networks. The first bits in a packet can arrive at a router while many of remaining bits in the packet are still waiting to be transmitted by the preceding router. If a picture speaks 1,000 words, then the animation must speak 1,000,000 words. The companion website for this textbook provides an interactive Java applet that nicely illustrates and constant transmission delay and propagation delay. The reader is highly encouraged to visit the applet. Smith 2009 also provides a very readable discussion of propagation, queuing, and transmission delays. If we let propagation delay, queuing delay, transmission delay, and propagation delay, the total delay is sum of all these. The contribution of these delay components can vary significantly. For example, propagation delay can be negligible, for example, a couple of microseconds for a link connecting two routers on the same university campus. However, propagation delay is hundreds of milliseconds for two routers interconnected by a geostationary satellite link and can be dominant term in nodal delay. Similarly, transmission delay can range from negligible to significant. Its contribution is typically negligible for transmission rates of 10 Mbps per second and higher, for example for LANs. However, it can be hundreds of milliseconds for large internet packets sent over a low-speed dial-up modem links. The processing delay is often negligible. However, it strongly influences a router's maximum throughput, which is maximum rate at which a router can forward packets.
Queuing delay and the packet loss. The most complicated and interesting component of the nodal delay is the queuing delay, DQ. In fact, queuing delay is so important and the interesting in networking. The thousands of the papers and numerous books have been written on it. We have given a very only high level intuitive discussion of the queuing delay here. The more curious reader want to browse some books. Okay, unlikely the other three delays, the DQ delay can vary from packet to packet. From the 10 packets arrive at any empty queuing at the same time, the first packet transmitted will suffer on no queuing delay. Will be the last packet transmitted will suffer a relative large queuing delay. Therefore, when characterizing queuing delay, one typically uses statistical measures such as average queuing delay, variance of queuing delay, and the probability that the queuing delay exceeds some specified value. When is the queuing delay large and when is the insignificant? The answer to this question depends on the rate at which traffic arrives at the queue, the transmission of the rate link, the nature of the arriving traffic, that is whether the traffic arrives periodically or arrives in bursts. To gain some insight here, donate the average rate of the which packets arrives at the queue. Recall the R transmission rate and the R rate in bits per second. and it pushed a queue. Also suppose for simplicity that all packets consist of L bits, then the average rate at the which bytes arrive as the queuing as a L bar A. Finally, assume that queue is very big, so it can handle only infinite number of ratios. The L bar are the called the traffic intensity. Often plays an important role estimating the extent of the queuing delay. Then the average of the rate of the bits of arrive to queue exceeds the rate of the bits transmitted from the queue. An unfortunate situation, the queue will tend to increase without bound and queuing delay will approach infinity. Therefore, the one of the golden rule in traffic engineering, delay will approach infinity. Therefore design your system so traffic intensity is no greater than 1. Now consider the case LR by 1. Either the nature of arriving traffic impact queuing delay. For example, if the packet arrives periodically, that is one packet arrives L bar R seconds, then every packet will arrive at this empty queue and there will be no queuing delay. On the other hand, if packet arrives in a burst but periodically, there can be a significant average queuing delay. For the example, suppose n packets arrives simultaneously every L bar an second, then the packet transmitted has no queuing delay. The packet transmitted has no queuing delay L bar r seconds, and more generally the nth packet transmitted has queuing delay of the n minus 1 L bar seconds. We leave it at the exercises of the relations of queuing delay. The two examples of the periodic arrival of the describing above the bit of seconds. Typically, the arrival process of the queuing of the queue is random. There is a arrival do not follow any patterns. The packet are spaced up apart from the random amount of the time. There are more related cases available are not usually sufficient to full characterize queuing delay statistics. Nonetheless, the useful gaining is the institutional understanding the extent of the queuing delay. The particular traffic intensity close zero. The packet arrival at the few far between the unlikely to then arriving the packets. Find will be another packet in the queue. Hence, the average queuing delay will be the packet will be another queue. B also 0. On the other hand, when the traffic intensity is close to 1, there will be intervals of the time when the arrival rate exceeds the transmission capacity due to variation of the packet's arrival rate, and a queue is will be the duration of these period times. When the arrival of the rate is less than transmission capacity, the length of the queuing will be shrunk. Nonetheless, the traffic intensity approaches 1, the average queuing length is larger and larger. The quantitative average queuing delay on the traffic intensity is shown in figure 1.8. Depends of the figure 1.8 dependence of the average queuing delay on the traffic intensity. One of the most important aspect is 1.8. The traffic approaches 1. The average queuing delay increased rapidly. A small percentage increase in the intensity will result in a much larger percentage wise increased delay. Perhaps the experience phenomena this way: if it regularly drive around the road, it typically congested. The fact of the road typically congested means the traffic is constantly in close to 1. If it is some of the events cause an average slightly larger than usual amount, the delay of your experience can be huge. To really get a good feel of the forward queuing, you are encouraged to once visit company website which provides an interactive Java applet for queue. If you set packet of the arrival high enough, intensity exceeds, you will see the queuing slowly build up over time. Packet loss. In the other discussion above, we have assumed the queue is capable of holding infinite number of packets. In reality, queue presets a link of the finite capacity. Also, queue capacity greatly depends on the router design and the cost. Because the queuing capacity is finite, packets do not approach infinity. The traffic intensity approaches 1. Intense packet can be arrive to the full queue with no place to store such a packet. A router will drop the packet, that is the packet will be lost. Their overflow at the queue is the Java applet. The traffic intensity is greater than 1. From the end system viewpoint, packet loss will be packet having been transmitted in network core but never emerges with the network at the destination. The fraction of the lost packet increases as the traffic intensity increases. Therefore, performance at the node of the measured not only in the terms of delay but also in the term of the probability of packet loss, as we will see in discussion subsequent chapter. As a packet loss and a lost packet may be read, transmitted, and end-to-end basis of the order ensure all the data eventually transferred from the source to destination.
Let us start the next topic called as end-to-end delay, in which one end we have source and another end we have destination. So the total delay from source to destination is called as end-to-end delay. Consider there are n-1 routers between source host and destination host. The processing delay at each router and at the source host is given by D processing delay. The transmission rate out of each router and out of the source host is given by capital R, that is capital R is equal to bit by second, and the propagation on each link is given by D propagation. So combining all these factors, the end-to-end delay formula is small d end-to-end is equal to n bracket d processing delay plus d transmission rate plus d propagation bracket complete, where d transmission is equal to L by R, where L is represents packet size. Moving on to the next subtopic called as trace route. So let us see how it works. Traceroute is a simple program that can run in any internet host. When the user specifies a destination host name, the program in the source host sends multiple special packets towards that destination. As these packets work their way toward the destination, they pass through a series of routers. When a router receives one of these special packets, it sends back to the source a short message that contains the name and address of the router. More specifically, suppose there are n-1 routers between the source and the destination. Then the source will send n special packet into the network with each packet addressed to the ultimate destination. These n special packets are marked as 1 through capital N, with the first packet marked first and the last packet marked as N. When the nth router receives the nth packet marked N, the router does not forward the packet towards its destination but instead sends a message back to the source. When the destination host receives the nth packet, it too returns a message back to the source. The source records the time that elapses between when it sends a packet and when it receives the corresponding return message. It also records the name and address of the that returns the message. In this manner, the source can reconstruct the route taken by packets flowing from source to destination, and the source can determine the round trip delays to all the intervening routers. Trace route actually repeat the experiment just described 3 times. So the source actually sends 3n packet to the destination. RFC 1393 describes about trace route in detail. So if anybody want to try out trace route program, they can visit the site www.traceroute.org, which provides a web interface to an extensive list of sources for route tracing. You choose a source and supply the host name for any destination. The trace route program then does all the work. There are a number of free software programs that provides a graphical interface to trace route. One of is that ping plotter. Moving on to the subtopic that is about end system application and other delays. In addition to processing, transmission and propagation delays, there can be additional significant delays in the end system. For example, an end system wanting to transmit a packet into shared medium may purposefully delay its transmission as part of its protocol for sharing medium with other end system. Another important delay is
Media packetization delay, which is present in voice over IP, that is VoIP applications. In VoIP, the sending side must first fill a packet with encoded digitized speech before passing the packet to the internet. This time to fill a packet, called the packetization delay, can be significant and can impact the user perceived quality of VoIP call.
Next topic is throughput in computer networks. In addition to delay and packet loss, another critical performance measure in a computer network is end-to-end throughput. To define throughput, consider transferring a large file from host A to host B across a computer network. For example, a large video clip from one pair to another in a P2P file sharing system. The instantaneous throughput at any instant of time is the rate at which host B is receiving the file. If the file consists of F bits and the transfer takes T seconds for host B to receive all F bits, then the average throughput of file transfer is F per T. For some applications such as internet telephony, it is desirable to have a low delay and an instantaneous throughput consistently above some threshold. For other applications, including those involving file transfer, delay is not critical, but it is desirable to have the highest possible throughput. To gain further insight into the important concept of throughput, let's consider for a few examples. The above figure shows the two end-to-end systems, a server and client connected by two communication links and router. Consider the throughput for file transfer from a server to client. Let RS denoted the rate of link between server and router, and RC denoted the rate of link between router and client. Suppose that the only bits being sent in an entire network are those from server to client. We now ask, in this idea, what is the server to client throughput? To answer this question, we may think of bits and communication links as pipes. Clearly, the server cannot pump bits through its link at a rate faster than RS, and router cannot forward bits at rate faster than RC. RS is lesser than RC. Then the bits pumped by several server with flow right through the router and arrive at a client at rate of RS BPS, giving a throughput of RS. If on other hand RS is lesser than RS, then the router will not be able to forward bits quickly as it received them. In this case, bits will only leave the router at rate RC, giving an end-to-end throughput of RC. Thus, for this simple two-link network, the throughput in minimum RC and RS, that is, it is the transmission rate of link. Having determined the throughput, we can now approximate the time it takes to transfer a large file of F bits from server to client as F. For a specific example, suppose you are downloading an MP3 file of f equal to 32 million bits. The server has a transmission rate of rs equal to 2 mbps and you have an access link of rc equal to 1 mbps. The time needed to transfer the file is then 32 seconds. Of course, these expressions for throughput and transfer time are only approximation as they do not account for store and forward and processing delays as well as protocol issue. The above figure shows a network with end links between the server and client, with the transmission rates of the end links being R1 to Rn, applying the same analysis as for the two link network. We find that throughput for a file transfer from server to client is minimum R1 to Rn, which is once again the transmission rate of bottle link along the path between server and client. Now consider another example motivated by today's internet. Shows two end system, server and client, connected to computer network. Consider the throughput for file transfer from server to client. The server is connected to network with an access link of rate rs and client is connected to the network with access link of rate rc. Now suppose that all the links in the core of communication network have very high transmission rate, much higher than RS and RC. Today the core of internet is over which high speed links that expands little. Also suppose that the only bits being sent in entire network are those from server to client because the core of the computer network is linked wide pipe. In example, the rate at which bits cannot flow from source to destination is again minimum of rs and rc, that is throughput minimum rc and rs. Therefore containing factor for throughput in today's internet is typically the access network. For final example, consider above figure in which there are 10 servers and 10 clients connected to core of the computer network. In this example, there are 10 simultaneous downloaders taking place involving 10 client server pairs. Suppose that these 10 downloaders are the only traffic in network at current time. As shown in a figure, there is link in core that traversed by all 10 downloads. Denoted R from transmission rate of these link R. Let's suppose that all server access link have same rate rs, all client access link have the same rate rc, and transmission rates of all the links in a core except the one common link of rate are much larger than rc and rs. Now we ask, what are throughputs of the downloads? Clearly, if the rate of common link R is large, say 100 times larger than both RS and RC, then throughput from each download which once again be minimum RS and RC. But what if rate of common link is of some order as RS and RC? What will the throughput be in this case? Let's take a look at specific example. Suppose Rs equal to 2 Mbps, Rc equal to 1 Mbps, R equal to 5 Mbps, and common link divided its transmission rate equally among the 10 downloads. Then for each download is no longer in access network but is now instead shared link in the core, which only provides each download with 500 kbps of throughput. Thus the end-to-end throughput for each download is now reduced 500 kbps. The example of both show that throughput depends on transmission rate of link over which the data flows. We saw that when there is no other traffic, the throughput can simply be approximated as the minimum transmission rate along the path between source and destination. The example show that more generally the throughput depends not only the transmission rate of links along the path but also an intervening traffic. In particular, a link with high transmission rate may nonetheless be the link for file transfer. In many other data flows are also passing through that link. We will examine throughput in computer networks more closely in the homework problems and in subsequent chapter.
Protocol layer and their service models. From our discussion thus far, it is apparent that Internet is an extremely complicated system. We have seen that there are many pieces of Internet, numerous applications and protocols, various types of end system, packet switches, and various types of link level media. Given this enormous complexity, is there any hope of organizing a network architecture, or at least our discussion of network architecture? Fortunately, the answer to both the question is yes. Layer architecture. Before attempting the organization, our thoughts on Internet architecture, let's look for the human analogy. Actually, we deal with complexity systems all the time in our day life. Imagine if someone asked you to describe, for example, the airline system. How would you find the structure to describe the complex system that has ticketing agents, baggage checkers, gate personnel, pilots, aeroplanes, air traffic control, and the worldwide system for routing aeroplanes? One way to describe this system might be describe the series of actions you take when you fly in a airline. You purchase your ticket, check your bags, go to the gates, and eventually get loaded into the plane. The plane takes off and routed to this destination. After your plane lands, you deplane at the gate and claim your bags. If the trip was bad, you complain about the flight to the ticket agents, getting nothing for your effort. This scenario as shown in the figure 1.21. Already we can see some analogies here with the computer networking. You are being shipped source to destination by the aeroplane. A packet is shipped from source host to destination host in the internet. But this is not quite the analogy we are after. We are looking for some structure in the figure 1.21. Looking at the figure 1.21, we note that there is ticketing function at each end. There is also baggaging function for already ticketed passengers and gated function for already ticketed and already badged checked passengers. For passengers who have made it through the gate, there is a takeoff and landing function,
and while the flight there is an aeroplane routing function. This suggests that we can look the functionally in the figure 1.21 in horizontal manner as shown in the 1.22 figure. Figure 1.22 has divided aeroline functionally into layers, providing a framework in which we can discuss airline travels. Note that each layer combined with the layer below it implements so functionally some services, a ticket that agents at the ticketing layer and the below the airline counter to airline counter. Transfer a personal accomplished at the badge layer and the below badge check to badge. Claim transfer person at the back is accomplished. Note that the baggage layer provides these services only to an already ticketed persons. At the gate layer, departure gate to arrival gate transfer for the persons and bag is accomplished. At this takeoff or landing layer, runway to runway transfer of the people and their bags is accomplished. Each layer provides its services by performing certain actions with the layer and by using the services of the layer directly below. For example, in the gate layer using the runway to runway passenger transfer service of the takeoff or landing layer. A layer architecture allows us to discuss well-defined specific part of the large and complex system. This specification itself a considerable value by providing modularity, making it much easier to change implementation of the service provided by the layer. As long as layer provides some the services to the layer above it and uses some services from the layer below it. The remainder of the system remains uncharged when the layer implementation is changed. Note that changing the implementation of the services is very different from changing the service itself. For example, if the gate function were changed, for instance, to have people board from and dismarkable by it, remember of the airline system would remain unchanged since the gates layer still provides some function. It simply implements the function is an different manner after change for large complex systems that are consistently being uploaded, and ability to change the implementation of the services without affecting other components of the system is another important advantages of layering. Protocol layering. But enough about airlines, let we turn our attention to the network protocols. To provide structure and design of network protocol, network designer organize protocols and network hardware and the software that implements the protocol in layers. Each protocol belonging to one layer just as a function in the airline architecture in figure 1.22 belonging to the layer. We are again interested in the services that layer offers us to layer above, the so-called service model of the layer. Just as in the case of our airline example, each layer provides its services by performing certain actions within that layer and by using the services that layer directly below it. For example, the service provided by the N may include reliable delivery of messages from one edge to network to other. It might be implemented by using the irreliable edge-to-edge message delivery services of layer N-1 and adding layer N functionally to detect the retransmit lost messages. A protocol layer can be implemented in the software and hardware or combination of the both two. Application layer protocols such as HTTP and SMTP are almost always implemented in the software in the end systems. So are the transport layer protocols, because the physical layer and the data link layer are responsible for handling communication over the specific link. They are typically implemented in the network interface, for example Ethernet and the Wi-Fi interface cards. Associated with the given link, the network layer is often to mix implementation of hardware and the software. Also note that just a function is layered airline architecture was described among the various airports and flight control centers that make up the system. So too the layer N protocol distribute among the end system, packet switches and other components that make up the network. That is there often piece of layer N protocol in each of these network components. Protocol layer has the conceptual and the structural advantages. RCFC 3439 as we seen layering provides such a way discuss system components. Modularity makes it easier to update system components. We mention however that some researchers and networking engineers are vehemently opposed the layering. On potential drawback of layering is that one layer may duplicate the lower layer functionality. For example, many protocol stack provide error recovery on the both per link basis and the end-to-end basis. The second potential drawback is functionally at one layer may need information, for example the timestamp value, that is present only in the another layer. This violates the goal of separation of layers. We taken together the protocol of various layers is called the protocol stack. The Internet protocol stack consists of 5 layers: physical layer, link layer, network layer, transport layer and application layer. As shown in the figure 1.23, if you examine table of contents, you will see that have roughly organized this book using layer of the Internet protocol stack. We take a top to bottom approach. First covering the application layer and the proceeding downwards.
Application layer is where network application and their application layer protocols reside. The Internet's application layer includes many protocols such as HTTP protocol, which provides for web documents required and transfer, SMTP, which provides videos for the transfer of email messages, and FTP, which provides for the transfer files between two end systems. We will see that certain network functions such as translation of human-friendly names for Internet end systems like WWIETF organization to 32-bit network address are also done with the help of specific application layer protocol, namely the domain name system. We will see in chapter 2 that is very easy to create and develop own new application layer protocol. An application layer protocol is distributed over multiple end systems with application in one end system using the protocol to exchange packets of information with the application in another end system. We will refer to this packet of information at the application layer as a message. Transport layer. Internet transport layer, application layer messages between application endpoints. In the Internet, there are two transport protocols, TCP and UDP, either of which can transport application layer messages. TCP provides a connection-oriented service to its application. This service includes guaranteed delivery of application layer messages to the destination and flow control. TCP also breaks long messages into shorter segments and provide a conjugation control mechanism so that is a source throttles its transformation rate when the network is congested. The UDP protocol provides a connectionless service to its application. This is a no frills service that provides no reliability, no flow control and no congestion control. In this book, we will refer to a transport layer packet as a segment. Network layer. Internet's network layer is responsible for moving network layer packets known as datagrams from one host to another. The Internet transport layer protocol in a source host passes transport layer segment and destination address to the network layer, just as you would give the postal service a letter with destination address. The network layer then provides a service of delivery in the segment to the transfer layer in the destination host. The Internet network layer includes the celebrated IP protocol, which defines the field in the datagram as well how the end system and routers act on the fields. There is only one IP protocol, and all Internet components that have network layer must run the IP protocol. Internet layer networks layer also contain routing protocols, determines the routes that datagrams take between source and destination. Internet has many routing protocols. As we saw in session 1.3, Internet is a network of networks. Within the network administrator can run any routing protocol desired all through the network layer containing both IP protocol and numerous routing protocols. It is often simply referred to as a IP layer, reflecting the fact that IP glue that binds the Internet together. Link layer. Internet network layer routes a datagram through the series of routers between the source and destination. To move the packets from one node to the next node in a route, the network layer releases one service of link layer. In particular, at each node, the network layer passes the datagrams down to the link layer, which delivers the datagram to next node along the route. At this next node, the link layer passes the datagram up to the network layer. The service provided by the link layer depends on the specific link layer protocol that is employed over the link. For example, some link layer protocol provides a reliable delivery from transmitting node over one link to receiving node. This reliable delivery service different from reliable delivery service to TCP, which provides reliable delivery from one end system to another. Example link layer protocols includes Ethernet, Wi-Fi, and cable access networks protocols. As datagram typically need to travels several links to travel from source to destination. Datagram may handle by different link layer protocols at the different link along its route. For example, datagram may be handled by Ethernet one link and by PPP on the next link. The network layer will receive different service from each of the different link layer protocol. In this book, we will refer to the link layer packets as the frames. Physical layer. While the job of the link layer is to move entire frames from one network element to adjacent network element, the job of the physical layer is to move the individual bytes within the frame from one node to another next. Protocol in this layer are again link dependent and further dependent on the actual transmission medium of the link. For example, Ethernet has many physical layer protocols. One for twisted pair copper wire, another coaxial cable, another for fiber, and so on. Each case, bit is moved across the link a different way. Next, the OSI model. Having discussed Internet protocol stack in detail, we should mention that it is not only protocol stack around, and in particular back in late 1970s, International Organization for Standardization preferred the computer networks organized around 7 layers called Open System Interconnection Model. The Open ISO model took shape when protocols that were becoming the Internet protocols were their influence and were but one of many different protocol suites under development. In fact, inventors of the original OSI model probably didn't have any Internet in mind when creating it. Nevertheless, beginning in the late 1970s, many training and university courses picked up one of the ISO maintained and organized course around the 7-layer model because of its early impact on networking education. 7-layer model continues to linger on in some networking textbooks and training source. The 7 layer of the OSI reverse model shows in figure 1.23. are application layer, presentation layer, session layer, transportation layer, network layer, data link layer, and physical layer. Functionality of 5 of the layer is roughly as the same their similar name network. This let's consider two additional layers present in the OSI refer model: presentation layer and session layer. The role of the presentation layer is to provide service that allows communicating application to interpret the meaning of data exchange. This service includes the data compression and data encryption, as well data description. The application from having to worry about internal format in which data are represented, format that may differ from one computer to another. The session layer provides the delimiting and synchronization of data exchange, including the mean to build checkpointing and recovery scheme. The fact that the internet lacks two layers found in the OSI refers model poses a couple of interesting questions. Are the service provided by these layers important? What is application need to one of the service? Internet's answer to both these questions in the same. It's up to the application developer. It's up to the application developer to decide if service is important. If the service is important, it's up to the application developer to build the functionality into the application.
Section 1.5.2 Encapsulation. The figure 1.24 shows the physical path that data takes down a sending end systems protocol stack, up and down the protocol stack of an intervening link layer switch and router, and then up the protocol stack at the receiving end system. As we discuss later in this book, routers and link layer switches are both packet switches. Similarly to end systems, routers and link layer switches organize their networking hardware and software into layers. But routers and link layer switches do not implement all of the layer in the protocol stack. They typically implement only the bottom layers. As shown in the figure 1.24, link layer switches implement layer 1 and 2. Router implements layer 1 through 3. This means, for example, that internet routers are capable of implementing the IP protocol, that is a layer 3 protocol, while link layer switches are not. We'll see later that while link layer switches do not recognize IP address, they are capable of recognizing layer 2 address such as Ethernet address. Note that hosts implement all 5 layers. This is consistent with the view that the internet architecture puts much of its complexity at the edge of the network. The figure 1.24 also illustrates the important concept of encapsulation at the sending host. An application layer message that is M in the figure 1.24 is passed to the transport layer. In the simplest case, the transport layer takes the message and appends additional information, that is so-called transport layer header information, that is HT in the figure 1.24, that will be used by the receiver side transport layer. The application layer message and the transport layer header information together constitute the transport layer segment. The transport layer segment thus encapsulates the application layer message. The added information might include information allowing the receiver side transport layer to deliver the message up to the appropriate application, and error detection bits that allow the receiver to determine whether bits in the message have been changed in route. The transport layer then passes the segment to the network layer, which adds network layer header information, that is HN in the figure 1.24, such as source and destination end system addresses, creating a network layer datagram. Datagram is then passed to the link layer, which of course will add its own link layer header information and create a link layer frame. Thus, we see that at each layer, a packet has two types of field, header field and a payload field. The payload field is typically a packet from the layer above. A useful analogy here is the sending of an inter-office memo from one corporate branch office to other via the public postal service. Suppose Alice, who is in the branch office, wants to send a memo to Bob, who is in the another branch office. The memo is analogous to the application layer message. Alice puts the memo in an inter-office envelope with Bob's name and department written on the front of the envelope. The inter-office envelope is analogous to a transport layer segment. It contains header information, that is Bob's name and department number, and it encapsulates the application layer message, that is the memo. When the sending branch office mailroom receives the inter-office envelope, it puts the inter-office envelope inside yet another envelope, which is suitable for sending through the public postal service. The sending mailroom also writes the postal address of the sending and receiving branch offices on the postal envelope. Here, the postal envelope is analogous to the datagram. It encapsulates the transport layer segment, that is the inter-office envelope, which encapsulates the original message, that is the memo. The postal service delivers the postal envelope to the receiving branch office mailroom. There, the process of de-encapsulation is begun. The mailroom extracts the inter-office memo and forward it to Bob. Finally, Bob opens the envelope and removes the memo. The process of encapsulation can be more complex than that described above. For example, a large message may be divided into multiple transport layer segments, that is, which might themselves each be divided into multiple network layer datagrams. At the receiving end, such a segment must be reconstructed from its constituent datagrams.
6.1 Network under attack. The internet has become mission critical for many institutions today, including large and small companies, universities, and government agencies. Many individuals rely on the internet for many of their professional, social, and personal activities. But behind all of this utility and excitement, there is a dark side, a side where bad guys attempt to wreak havoc in our daily lives by damaging our internet connected computers, violating our privacy, and rendering inoperable the internet service on which we depend. The field of network security is about how the bad guys can attack computer network and how we, soon to be experts in computer networking, can defend network against those attacks, or better yet, design new architecture that are immune to such attacks in the first place. Given the frequency and variety of existing attacks, as well as the threat of new and more destructive future attacks, network security has become a central topic in the field of computer networking. One of the features of this textbook is that it brings the network security issue to the forefront. Since we don't yet have expertise in computer networking and internet protocol, we will begin here by surveying some of the today's more prevalent security related problems. This will whet our applied for more substantial discussion in the upcoming chapter. So we will begin here by simply asking what can go wrong, how are computer network vulnerable, what are some of the more prevalent types of attacks today. The bad guys can put the malware into your host via the internet. We attach devices to the internet because we want to receive, send the data from to the internet. This includes all kind of good stuff including web pages, email messages, MP3 songs, telephone call, live video, search engine, result and so on. But unfortunately, along with all the good stuff come the malicious stuff collection collectively known as malware that can also enter then infect our devices. Once the malware attacks our devices, it can do all kind of devilish things including deleting our files, installing spyware that collects our private information such as social security number, password and keystrokes, and then send this over all the internet. Of course, back to the bad guys, our compressed host may also be enrolled in the network of thousands of similarly compressed devices, collectively known as botnet. Which of the bad guys control the leverage and spam, email distribution or distribution denial of the service attack, soon to be discussed against the targeted host. Much of the malware out there today is self-replicating. Once it infects one host, from the one host it seeks the entry to the other host over the internet, and from the newly infected host it seeks the entry into yet more hosts. In this manner, self-replicating malware can spread exponentially fast. Malware can spread in the form of various viruses or the worms. Viruses are the malware that require some form of user's interaction to interact the user devices. The classic example is an email attachment containing the malicious executable code. If the user receives and opens such attachments, if the user inadvertently runs the malware on the devices. Typically, such emails, viruses, and self-replicating once execute, the virus may send an identical message with an identical malicious attachment to it. For example, every recipient in the user address book. Worms are the malware that can enter the devices without any explicit user interaction. For example, a user may be running a vulnerable network application to which an attacker can send a malware. In some cases, without any user intervention, the application may expect the malware from the internet. Creating a worm. A worm in the newly infected devices, then scans the internet searching for the other host running the same vulnerable network application. When it finds the other vulnerable host, it sends a copy to itself to those hosts. Today, malware is previously and costly to defend against. As you work through this textbook, we encourage you to think about the following questions. What can computer network designer do to defend internet attached devices from malware attacks? The bad guys can attack servers and the network infrastructure. Another broad class of security threats are known as denial of services attacks. As the name suggests, a DOS attack renders a network host or other piece of infrastructure unusable by legitimate user. Web servers, email services, DNS service, and the illustration network can all be subject to DOS attacks. Internet DOS attacks are extremely common, with thousands of DOS attacks occurring every year. Most internet DOS attacks falls into one or three categories. The first one, vulnerability attack. This involves sending a few well-crafted messages to a vulnerable application or operating system running on a targeted host. If the right sequence of the packet is sent to the vulnerable application or operating system, the service can stop, or worse, or the host can crash. The second one, bandwidth flooding. The attacker sends the glitch of the packet or to the targeted host so many packets that the targeted access link become clogged, preventing legitimate packets from the reaching the server. The third one, connection flooding. The attacker established a large number of half-open or fully open TCP connection. TCP connections are discussed in chapter 3. At the target host, the host can become so blocked down with these blocked connections that stops expecting legitimate connection. Now, let us explore the bandwidth flooding attack in more detail, recalling our delay and loss analysis discussion in section 1.4.2. It's evident that we can use the server as an access rate of Rbps, then the attackers will need to send traffic at the rate of X approximately Rbps to cause the damage. If R is very large, a single attack source may not be able to generate enough traffic to harm the server. Furthermore, if all the traffic emanates from the single resource, the upstream route may be able to detect the attack and block the traffic from the source. Before the traffic gets near the server in the distribution DOS, the attacks illustrated in the figure 1.2.5, the attacker controls the multiple resources and has the each source blast traffic at the target. With this approach, the aggregated traffic rate across the controlled resources needs to be approximately R to cripple the services. The DOS attacks leverage botnets of thousands of compressed hosts are the common occurrences today. DOS attacks are much harder to detect and defend against than the DOS attacks from the single host. We encourage you to consider the following questions as you work your way through this book. What can the computer network design to defend against DOS attacks? We'll see the different defenses and need to for the three types of DOS attack.
The bad guys can sniff packets. Many users today access the internet via wireless devices such as Wi-Fi connected laptops or handheld devices with cellular internet connections covered in chapter 6 with ubiquitous internet access is extremely convenient and enables marvelous new applications for mobile users. It also creates a major security vulnerability by placing a passive receiver in the vicinity of the wireless transmitter. That receiver can obtain a copy of every packet that is transmitted. These packets can contain all kind of sensitive information, including passwords, social security numbers, trade secrets, and private personal messages. A passive receiver that records a copy of every packet that files is called a packet sniffer. Sniffers can be deployed in wide environments as well. In wide broadcast environments, as in many Ethernet LANs, a packet sniffer can obtain copies of broadcast packets sent over the LAN. As described in the section 1.2, cable access technologies also broadcast packets and others vulnerable to sniffing. Furthermore, a bad guy who gains access to an institution's access router or access links to the internet may be able to plant a sniffer that makes a copy of every packet going to or from the organization. Sniffed packets can then be analyzed offline for sensitive information. Packet sniffing software is freely available at the various websites and as commercial products. Professor teaching a networking course have been known to assign lab exercise that involve writing a packet sniffing and application layer data reconstruction program. Indeed, the Bioshock 2012 labs associated with with this text. See the introductory Bioshock lab at the end of this chapter. Use exactly such a packet sniffer because packet sniffers are passive. They do not inject packets into the channel. They are difficult to detect, so when we send packets into wireless channel, we must accept the possibility that some bad guy may be recording copies of our packets. As you may have guessed, some of the best defenses against packet sniffing involve cryptography. We will examine cryptography as it applies to network security in chapter 8. The bad guys can masquerade as someone you trust. It is surprisingly easy. You will have knowledge to do shortly as you proceed through this text. To create a packet with an arbitrary source address, packet content and destination address, and transmit this handcrafted packet into the internet, which will dutifully forward the packet to its destination. Imagine unsuspecting receiver, say the internet router, who receives such a packet takes the false source address as being truthful and then performs same command embedded in the packet's content, same modifies its forwarding table. The ability to inject packets into the internet with a false source address is known as IP spoofing. It is but one of the many ways in which one user can masquerade as another user. To solve this problem, we all need endpoint authentication to solve the masquerade as another user. But one ways in which one user can masquerade as another user. To solve this problem, we need endpoint authentication, that is mechanism that will allow us to determine the certainty of a message where we think it does. Once again, we encourage you to think about how this can be done for network application and protocol as you progress through the chapters of this book. We will explore mechanism of the endpoint authentication in chapter 8. In closing section, it was considering how internet go to such an insecure place in the first place. The answer in the essence is that the internet was originally designed to be that way based on the model of the group of manually trusting users attached to a transparent network. Blumenthal 2001, a model in which by definition there is no need for security. Many aspects of the original internet architecture deploy reflects this notion mutual trust. For example, the ability for one user to send a packet to any other user is default rather than a requested or granted capability, and user identity is taken a declared face value rather than being authenticated by default. But today's internet certainly does not involve mutually trusting users. Nonetheless, today users still need to communicate when they don't necessarily trust each other. May wish to communicate anonymously, may communicate indirectly through third parties, example web caches, which we will study in chapter 2, or modify assisting agents, which we will study in chapter 6, and may disturb the hardware, software, and even air through which they communicate. We know we have many security related challenges before as we progress through this book. We should seek defense against sniffing, endpoint masquerading man in the middle attacks, DDoS attacks, malware, and more. We should keep in mind that communication among mutually trusted users is exception rather than the rule. Welcome to the world modern computer network.
The computer networks and the internet. Here we start. In this chapter, we have covered a tremendous amount of material. We have looked at the various pieces of hardware and software that make up the internet in particular and computer networks in general. We started at the edge of the network, looking at the end systems and applications, and at the transport service provided to the applications running on the end systems. We also looked at the link layer technologies and physical media typically found in the access network. We then dove deeper inside the network into the network core, identifying packet switching and circuit switching network into the network core. Identifying packet switching and circuit switching as the two basic approaches for transporting data through a telecommunication network. And we examined the strengths and weaknesses of each approach. We also examined the structure of a global internet, learning the internet is the network of networks. We saw that the internet's hierarchical structure, consisting of a higher and a lower tier IPS, Internet Service Protocols, has allowed it to scale to include thousands of networks. In the second part of this introductory chapter, we have examined several topics central to the field of computer networking. We first examined the causes of a delay, throughput, and a packet loss in a packet switched network. We developed a simple quantitative models for transmission, propagation, and queuing delays as well as throughput. We will make extensive use of these delays models in the homework problems throughout this book. Next, we examine the protocol layering and service models, key architectural principles in the networking that will also refer back throughout this book. We also survived some of the more prevalent security attacks in the internet day. We finished our introduction to networking with a brief history of computer networking. The first chapter in itself constitutes a mini course in computer networking. So we indeed covered a tremendous amount of ground in this first chapter. If you are a bit overwhelmed, don't worry. In the following chapters, we will revise it, all of these ideas, covering them in much more detail. At this point, we hope you leave this chapter while still developing intuitions for the piece that make up a network, a still developing command of a vocabulary of a networking, and ever-growing desire to learn more about networking. That's the task ahead of us for the rest of this book. And thank you.